All right, so here we're going to build on the previous video where we talked about languages in a mathematical sense, right? As a mathematical object. Now we're going to put those into an application here, right, on what are called a finite state automatons. Now, here it'll be beneficial to think of a compiler, right? In the sense, if you've ever written an if statement, right? So if you write an if statement, right, we have if. Right, so the way a compiler processes an if statement is once it sees if that this has been used, then it's expecting open parentheses, right? After the open parentheses, it expects some Boolean condition, right? Something to check whether it is true or false, right? And then after that, it expects this, right? At each stage, as it kind of parses through our string here, right, the language, it is looking for a particular state, right? And each new symbol moves it to a new state, right? If it receives what it's expecting, it moves on. If it doesn't, then it'll flag it, right? Some kind of error assumes, right? So it's kind of in essence what a finite state automaton is, right? This abstracts this idea, right? So let's actually switch here to the textbook just to kind of parse through the definition here. All right, so let's see. All right, so here if we look at FSA, a finite state automaton, then is a machine which takes as input a finite string of symbols from some alphabet, right, which defined in the previous video. There is a finite set of states in which the machine can find itself. The state it is in before consuming any input is called the start state. Some of the states are accepting or final, right? So the accepting state is where it ends. If the machine ends in such a state after completely consuming an input string, the string is said to be accepted by the machine. The actual function in the machine is described by something called a transition function, right? How do I know where to go, right, at a particular state? Which specifies what happens if the machine is in a particular state and looking at a particular input symbol. Okay. All right, so a lot going on there. Let's kind of parse through it, right? So what this boils down to is that a DFA here, a deterministic finite state automaton, right, or DFA, right? So that means that, and what I mean by deterministic, if I'm in a current state, there is exactly one next state, no ambiguity, right? Knows what to do next, right? Or I know what is the next state, right? And there's only a choice of, it can only go to one of those next states, depending on what the current state is. Okay, so here, our formal definition here is it's a 5-tuple, so not an ordered pair, not an ordered triple, but an ordered 5-tuple. Okay, so here, a DFA is a 5-tuple. Okay, that consists, which we call M, which consists of the 5 things Q, sigma, Q naught, delta, and F. So let's define what these things are. So Q is the set of a finite set of states. And then sigma is my input alphabet. Q naught comes from Q, but this is the start state, right? So I specify where I start. My start state. Right. F, which is again a subset of Q, right? And this is the set of accepting final states. Okay, so, and delta is an operation that takes on two things. It takes on an ordered pair, and it maps onto Q. Right, so it's what we call a transition function. Okay, it means that if I'm in state Q and the next symbol is A, right? So this ordered pair here, that's what this Q cross X here, a state and a string, right? Or a symbol, excuse me, not a string, a symbol from an alphabet, right? So we have delta Q A, right? And that equals to another state, Q prime, I'll call. So what that means is if I'm in state Q and the next symbol is A, then we move to Q prime. Now, in practice, we'll use star to signify a string instead of just a symbol from an alphabet, right? So it could be like A, B, C, D, right? And you'll work through each four of these, right? You'll work through what is QA, and then the result of that, what is that result, Q prime, B, C, D, etc. Right? I'll illustrate this with an example here. All right, so a couple things on this delta function. It must be a total function, so it's defined for every pair. Okay, no ambiguity involved here. All right, no state symbol pair is left undefined. It's deterministic, and what that means is given a current state and a current input symbol, there's exactly one way to go next. So in other words, this is unique, right? Once you've established the current state you're in, what the next input is, then there is only one place to go. Okay, that's what we mean by deterministic. All right, so for example here, let's take a look at here. Sample from our textbook, we're given a table here where we have P, Q, and R, and these are my states. And the alphabet I'm working with is the binary 0, 1. So these are my inputs. Okay, so we have P, Q, R, Q, R, R. Okay, so this is a DFA, right, that we define here, right, an ordered 5 tuple. So the states being P, Q, R. Right, the alphabet being 0, 1. Right. We're going to designate P as my starting, and then delta as my function, and I'll define delta in a second, and then my ending state F to be R. The set F consists of one element, that being R. Right, that is my accepting state. Okay. All right, and then the function I'll define here as delta P. So given this state, given an input of 0, I find myself back at P. All right, again, I'm reading these values from the table. All right, state P, input 0, leaves me at P. State Q, input 0, that leaves me at Q. Okay, and then state R, delta 0, gives me R. Delta P, input 1, then that gives me Q. All right, delta Q, input 1, that gives me R. And then delta R, input 1, that gives me R. Okay, now for the star one, so here we want star of P 0, 1, 0, 0. Okay, so the way that looks like is what this would be equal to. So we'll start with what is delta, All right, again, don't let that star confuse you here. It just says we'll start with our function, and then that first input being 0. So I'm at P0, that is equal to P. So the next would be delta P, right, what I'm left with, and then the next one is 1. All right, so P1, we see that is Q, right, and now we're at delta at the next one. Q is the state I'm in, and the next alphabet I'm gonna parse is 0, so Q0 is Q, and then lastly 0, delta Q 0, and that is Q. All right, so the resulting output there would be Q for this one. That would be the last step there. Okay. All right, sometimes it's beneficial to set up a diagram to kind of describe what's going on here. And what we call that is a transition diagram. Okay, so here it's a directed graph representing my DFA. So each state is a node or a circle. An arrow labeled A from state Q to state Q prime represents my function. Okay, and then the start state has an unlabeled incoming error, and accepting states are drawn with double circles. Okay, so what that means here is, let's say I wanted to illustrate this above DFA. Okay, so the way that would look, okay, so it'll be my DFA F, and then we just have an arrow out of nowhere coming from our starting state, which is P, and now let's label Q and R, and R is our accepting state. So the accepting state gets drawn like this, right, where it has two concentric circles. Okay, so what we see here is that if I start at P here, it can either go on to Q, depending on what the input is, right, or it could stay into itself, right? So it either goes here, or it loops back around here. Right, it goes on to Q if we get an output of 1, but it stays put, input of 1, it stays put if the input is 0. And the same thing here, right? Q goes on to R here, right? And then here, if you notice, once we're in R, we stay in R regardless of what the input is, right? So it stays here regardless of whether the next state is 0 or 1, right? And it stays in Q if the input is 0. So here, this is our transition diagram, right? These are my accepting states, drawn with a double circle. Okay. All right. Here, and this allows just a visual to allow us to kind of maybe trace the DFA, right? And we could see here that it's accepted, right? Kind of following it, you could see the way it's accepting. It reaches the accepting state if it has 2 1s. They don't have to be consecutive, right? Just 2 1s in general. All right? Okay. So we could trace the machine, right? In order for it to be accepted, it must reach its accepting state, right? So for example, my function example here, this would not be accepted, right? Q is not an element of F. So it does not reach its accepting state. Okay. But if we were to do, let's say, Q of, let's say, 0, 1, 1, P star 0, 1, 1. Okay. All right. So we start here, right? P. So delta P 0. That gets me back at P, right? Now I can just get it from my diagram here. So the next step is delta P1. Right? And that says, oh, okay. Next step, move on to Q. Right? So that means here the next step is delta Q1. Well, that moves on to R, and I've reached the accepted state. right? So this is accepted. All right, and then lastly, what if, again, start at P, what if we just had this, right? And again, you could see this, what will happen here, we get delta P of 1, right? That moves on to Q. So we get delta Q of 1, that's going to move on to R, and then now at R, it's the accepted state, so the next two ones are just R. So the whole resulting one here is R. Okay, so it reaches the accepted state. All right, so we'll wrap it up in the next video on how to design one of these DFA from scratch for a given language.